Everyone, I'd like to introduce you all to Professor Kochenderfer from Stanford's Department of Aerospace and Aeronautics. Thank you so much for being here today. My first question would be, would you like to simply introduce yourself and perhaps talk about your research areas?
Yeah, sure thing. So I've been a professor here at Stanford for the past 8 years, and it has been a real blast. I've gotten to know lots of students over the years. I'm the director of the Stanford Intelligent Systems Laboratory, or Sizzle. My graduate students call themselves Sizzlers, and we work on computational models and algorithms for decision making under uncertainty, with a special focus on safety critical systems like aircraft and automated. Interested in modeling of these kinds of problems, planning, so going from probabilistic models of these problems to a decision-making strategy. And we're also very interested in validation of these complicated systems. So we want to make sure that the systems are safe before they're deployed in the real world.
Thank you so much for sharing. That's a very niche and interesting area to be a part of. So moving on to my next question, I wanted to start with the topic of randomness and autonomous driving systems, both cars and aircraft. How do you create algorithms to model randomness? What's the experimental design behind that data collection? And how do you even define the experiment to begin with, the problem?
Right, so the systems that we build, whether they're for aircraft or for cars, they need to interact with the real world. And the real world has a tremendous amount of variability. There are other drivers on the road and pedestrians and so forth. And there is this inherent randomness. People don't always walk straight. Cars don't always follow the speed limit. And it's important to capture the variability that we see in that real life. So the approaches that we take need to account for this uncertainty. Now, different outcomes are more likely than others. So the approach that we take needs to take that into account. Like most of the time, aircraft fly straight, but sometimes they turn left or turn right. It's important to weigh the different possible futures appropriately. And to do that, we use the standard language of probability. So we use probability distributions, which assigns different weights to different kinds of outcomes. So those probabilistic models are used as input to our methodology. Our methodology is based upon optimization. We try to optimize different kinds of objectives, such as reaching our destination while also being very safe. And maybe there's some other secondary objectives like not accelerating or jerking the passengers around too much. So you asked about how do we collect this data?
Yeah, like the experimental design behind it.
Yeah, so we try to get the raw data of how people and how the environment behaves in naturalistic settings. So when we were working on aircraft collision avoidance systems, what we did was we collected the radar tracks from aircraft in the United States, from the Federal Aviation Administration and the Department of Defense. And then from that, we could build large statistical models of how aircraft behave when they encounter each other. For driving, there's no like centralized surveillance of ground vehicles, right? But there are some number of data sets available to the public, and some of those have been curated by places like KIT or Waymo and so forth. And my graduate students and undergraduates have been using those data sources to assess the safety of the systems they develop.
Interesting. It's interesting to hear how you get the information, get the data from different outcomes, and like you said, different data sets. So that's one thing. And it's also really fascinating to hear how you use probability distributions and outcomes to perfect your methodologies towards this project or this entire area of research. My next question is, how do you ensure safety during like these unpredictable, uncertain, random circumstances? Like how do imperfect sensors affect the safety of the overall system? Yeah.
Yeah, when you have imperfect sensors, your understanding of the world will inherently be imperfect, which means that not only do you have trouble knowing the current state of the world, but it makes it difficult to predict what will happen in the future. Now, when you're trying to decide how to maneuver your aircraft or a car, you need to be able to predict what will be happening in the future. And so if you have noise and so forth, that will make it more challenging. But we can adapt our decision-making strategies so that we're more conservative or more robust to noise in our sensors and occlusions and so forth. So that requires planning, accounting for the limitations in our sensors. Now, no matter what we do for any kind of complicated system, it's really difficult, if not impossible, to produce a system that is 100% safe. And the regulators understand this, right? The Department of Transportation understands this in the context of cars, and the International Civil Aviation Organization, they understand that you can't make the airspace 100% safe. So we strive for a very high level of safety, and it's important to really characterize where there are vulnerabilities in the system or limitations ahead of time, and really characterize what is the expected failure rate when deployed in the real world.
Absolutely, that makes perfect sense. I mean, yeah, it's a good thing they probably understand, like you said, that it can't be 100% safe. And of course, you're ensuring the highest level of safety through. Yeah, that makes sense.
There will always, I mean, there will
Some variability.
be accidents on the highway and so forth. The aim, though, is to always introduce technologies that will lower that rate. And one of the important ways of lowering that rate is providing robustness to sensor errors, greater robustness to uncertainty in the environment and the behavior of the other actors in the environment, whether they're pedestrians or other drivers.
Okay, that's interesting. So like to model and resemble the situation best in that sense, and taking into account a bunch of other factors. Of course, it's impossible to do all, but as much the highest level that is possible to achieve through research. Makes perfect sense.
There are definitely computational challenges when it comes to reasoning about all these possible futures, right? The further out you look, the computational complexity can grow exponentially, right? Unless you're very careful. And so a lot of our work is figuring out how to create algorithms that can scale up to these real world problems, that allow you to plan out over longer horizons while still accounting for uncertainty.
Right, that makes sense. Got it. My next question is, how do you model uncertainty that will happen in the future? I think that's similar to the previous one, but just in more detail.
So how do you model uncertainty in the future?
Yeah, well, try your best to model uncertainty in the future.
Yeah. So you generally need to make some kind of assumptions about the structure of the uncertainty. There are things known as these probability distributions, and these probability distributions are generally parameterized by some number of knobs, and you can tune those knobs to best reflect what you observe in your data set. And there are different kinds of metrics for measuring how well your models capture that uncertainty. So that there are metrics like log likelihood and many of these other technical kinds of definitions. But one approach that I find especially convincing is known as, well, it's a variation of the well-known Turing test from AI. So if our system is, or if our models are able to generate trajectories or simulations that look realistic, that are indistinguishable from recorded data, then we can have a good feeling in our heart that our models are appropriate. So that's an additional level of reassurance that our models are behaving as expected, in addition to a number of other technical metrics.
That's a fascinating procedure, yeah. My next question is, are there ways to train or insert AI with human experiences for handling these rare occurrences?
Yeah, so often the building of these systems requires both data as well as expert judgment. And there are different ways to go about fusing those two different sources of information. So as much as possible, we would like to kind of automate the optimization of the decision-making strategies. And then after that optimization, just validate that it's doing something appropriate and comparing it against human experiences or human judgment. And if there's a mismatch between what the optimized system does and what a human expert would say to do, then that requires some thought. Is it due to maybe an issue with the modeling of the system, or is it with the optimization of the system, or what? Or it could be that, well, actually, maybe upon further thought, the expert might be wrong in this particular kind of situation.
That's
But we want
interesting.
to have that dialogue during the design phase before
Right.
it's deployed in the real world.
Right. I was going to say that like during the design phase, and I'm sure it involves like a lot of trial and error, comparing it to the human actions and human judgment.
That's right. So a major challenge is that these applications of interest, like automated driving, they have there are a lot of edge cases. And so you can't try out every edge case and validate it against a human judgment. And so we have to figure out how to prioritize the human effort in ensuring that the system will be safe and perform as desired.
Makes sense. I mean, relating to this question, who is liable or responsible for the failure of safely handling these rare situations?
Well, I think there's still quite a bit of discussion on the topic of liability and autonomy. I think some would say that the existing laws are kind of adequate for assigning liability. But as an engineer, I would say that we need to do our part in ensuring that the algorithms we build are robust and safe. Sometimes in industry, there's a lot of pressure to ship a product, and which makes sense, right? You want your technology to benefit society as quickly as possible, but the validation process is super important. So sometimes when they talk about writing code, the actual writing of the code maybe takes only a small fraction of the time spent on the code, maybe like 10%, but 90% of it is spent debugging and making sure that the code behaves as expected. And it's even more significant when it comes to these complicated artificially intelligent systems.
No, I can possibly imagine. I mean, when I'm debugging my code, like you said, takes 90% of the time than simply writing it. So of course, with larger projects, I'm assuming, like you said, there'd be like a longer validation process to see if the technology is working out for public use or not. But like you said, the whole idea that corporations do, rightfully so, to some extent, emphasize or prioritize shipping the product early or again. So that's also relating to my next question. What's the trade-off between, operational efficiency and safety? In your opinion, like what's the correct way to kind of strike a balance between these two factors?
Yeah, this balance is really, really tricky, right? So for a lot of these safety systems, if the system, like if you're building an automated vehicle, if it throws on too many hard brakes, no one's going to use the system, right?
Mhm.
Um, but you also don't want to not brake to
Be
when
safe while, yeah.
it would help you be safe. So too many hard brakes, it's very inconvenient. Like it interrupts your operational efficiency. It can also actually be kind of unsafe if you're always slamming on your brakes. It can cause secondary accidents, being rear-ended or whiplash to the
Yeah,
passenger.
that's another perspective I didn't think of. Yeah, the
So
opposite.
yeah, getting that balance right is really tricky. We've worked on developing some tools for helping get that balance right. Um, so you identified two of the key properties that you want to balance, like operational efficiency and safety. But even within those two categories, there may be, dozens of different metrics that you might want to care about. And so that dimensionality can really complicate the design process. And so part of the challenge that we have been facing is how do you create more user-friendly tools for the designer?
Interesting. No, that makes sense. Absolutely. My last question is just about, are government policies generally supportive or encouraging of these advancements in technologies?
So
Like the Department of Transportation or yeah,
yeah, I mean
bureaucracies. Yeah.
there are really good people, really forward-looking people in these agencies. That they have a really tricky job to do, right? Their top priority, of course, is to ensure safety. And there has been, at least in aviation, an incredible safety record, right? And that they would rightfully want to preserve that, right? When there are, aircraft accidents, especially commercial, involving commercial airliners, the ripple effects of that is just enormous, absolutely enormous. And so they're doing what they can to keep the airspace safe. And the Department of Transportation also wants to keep our highways safe. Um, but we have these emerging technologies that may be able to bring additional safety benefit. But we don't yet have, or we're in the process of building trust in these systems. And it may be tempting to produce regulations. And regulations can be both helpful in terms of spurring the development of technology while also kind of putting the brakes on, overeager deployment and so forth as well. But a major challenge is that uh, it's really hard to regulate an emerging technology because you don't know where the technology will go, right? And it's just very difficult to predict advances, especially when it comes to AI and other related technologies. So it's tricky. They of course want to
Ensure
support
safety, yeah.
um, support new technologies, especially when it will bring safety benefits as well as operational benefits as well.
No, absolutely. And thank you for pointing that out. And you're right. I think the Department of Transportation does definitely, their goal, like you said, is to ensure the safety of the general public, and rightfully so, to keep that track record that they already have built pretty well. But like you said, these technologies can also really help advance the safety aspect of transportation. So that's a positive thing to look after. Yeah. Is there anything you'd like the general public to know more about, aviation and the Department of Transportation, and how technologies can be implemented to further ensure safety and operational efficiency?
I think maybe just ending on this one point, which the aviation in the United States just has this amazing track record, and the reason for that is because the industry as a whole, in partnership with government, um, learns from past mistakes. So every time when there is an incident, it's carefully investigated. They work really hard to draw as many lessons as possible that can be learned from the accidents. And when we want to see new deployments of technology, we need to take baby steps and be really careful in learning from mistakes, and trying to minimize the risk of mistakes by careful analysis during the design phase.
Absolutely. Thank you for mentioning that. It's just another question that came off the top of my head. I was just wondering too, what advice would you give to any sort of teenager or middle schooler who's interested in pursuing the intersection of, transportation and technology?
So for those of you who are interested in the intersection of transportation and technology, um, it will benefit from uh, developing good study habits and developing an interest in mathematics and statistics and optimization. What underlies AI is really a bunch of mathematics. And it turns out that the mathematics are unbelievably fun. Um, uh, Sometimes, depending on how it's taught, maybe not everyone arrives at the impression that mathematics can be so fun. But it's really about creativity and using it to explore new ideas and push frontiers in technology.
No, I tend to agree about your point about mathematics. And honestly, the beauty of math is that it can be implemented everywhere, whether, fee, the golden ratio, or transportation, or technologies, or even business and entrepreneurship. So yeah, definitely math can be used everywhere. And it's interesting to see how, the usage of mathematics and statistics to ensure the safety when working with transportation.
And also on top of that, learning how to work in teams. So good social skills, how to interact well with other people, how to work together as a team. The reality is that all of these deployments and technologies, it requires a lot of people working together effectively. And so developing those skills at a young age can go a long way in ensuring success.
Absolutely. That's great advice. Thank you so much for sharing. And thank you so much for your time today, Professor Kochenderfer. We really appreciate it.
Yeah, sure thing.